So we're looking at forces and motion investigation. So the pre-investigation you guys are going to do. All right, here says Joe needs to push a file cabinet across the room. So he begins here by just looking at it in scene 1. And then he begins to start pushing on the file cabinet. And at first, the thing doesn't move. All right, that's how it says right here. Cabinet not moving. And then in scene 3, he starts pushing it and the thing begins to slide. So A asks you to describe all the forces you think are acting on the cabinet in each scene. And then why do you think the file cabinet moves in 3 but not 1 or 2? And then if the floor was covered in ice, how would the motion of the cabinet change? Okay, I want you guys to basically, this is just off of your knowledge, your top of the head, your understanding of forces or what you think are forces. Okay, and then we're going to go in and investigate what's going on here. So after everyone has completed their pre-investigation, all right, now we're going to move on to the actual investigation now. We're going to be able to, at the end of this, identify when an object is being acted upon by what we call unbalanced forces, and then be able to predict the change in motion when a force is applied to an object. Okay, so it says here, open the force motion simulation. So if you click on that, it's going to hyperlink. Okay, it's going to send you to this guy here. So if everyone can do that.
Could you give everyone a Snapchat so you can watch the screen here?
Okay, so it says here, play with the first tab of the sim for a few minutes, get comfortable with the functions. Then, using the simulation for help, you can take screenshots or describe in words showing Joe the file cabinet and force arrows. So scene 1, Joe not pushing. So here is scene 1. Joe, my man, is not pushing. So what two forces are here? We have F sub G and F sub N. So what do you think G would be? Gravity, good. Force of gravity. So every object has mass. The force of gravity, all right, is basically an object's mass times gravity, and that gives you weight. So an object's mass does not change no matter where you go. You can go up to the top of a mountain, down to the lowest part of, if you know, you can drain the ocean, go down to the lowest part that we have, go to the moon. Your mass will not change. Physically, nothing changes, right? You have all that mass. But your weight changes depending on location, because mass times gravity gives us this, Fg, which is weight. The force of gravity is weight. So mass times gravity is weight. If so, here's a dumb little corny ass joke that may help you remember, all right, the difference. When someone says you want to lose weight, what should they actually want to do? Lose weight or lose mass? Lose mass. Okay, and then here's a quick way to lose weight would be to go to the moon. Why would that? Gravity is much less. So the number we would calculate for weight. So whatever your weight is in pounds, if you divide it by like 2.2, that's roughly your mass. So I'm like 95 kilograms. Times that, let's just say by -10, right, or just 10. That would be my like weight in newtons. So I'd be like 950 something newtons. If I went to the moon, I would still be that 95 kilograms, but my weight would be about 1/6 that, because gravity on the moon is 1/6 that. So we have force of gravity is another one. Now we have, there's another force here, which is F sub N, which is called the normal force. And normal force is when an object is perpendicular to a surface. So we have a flat surface here. If that's the case and the object is not moving, the normal force is going to basically be equal to the object's weight. It's supporting the object on whatever surface it's on. Now, these two vectors, what do you think you see about these two dudes? Opposite directions is big. When we were dealing with vectors in the beginning of the year, opposite directions, what did we do with them? You had two vectors in opposite directions. What could we do? Subtract. Good. So if you have two arrows opposite directions, we're going to subtract them. What else do we notice about this thing? Is it moving or not? It's not moving. So if it's not moving, what do you think the values of those forces are? When you add them together, it's going to be 0. So that means they would have to be equal, right? Does that make sense? So let's just say one of them is 100 newtons down. That means the normal force would have to be 100 newtons up. Because if there was an unbalance, there would have to be motion of some sort. When all the forces are balanced, this thing is either going to do one of two things: not move, or basically not change what it's doing. And by what I mean not change, it means it would have to go at a constant speed in a straight line, or AKA constant velocity. So if you guys did screenshot, I'm not 100% sure how to do it on the Chromebook. I think it's like control, then there's like a little square with like two lines next to it. All right, if you like hit that control print screen or the control box with the two lines, that copies whatever you're on your screen. So I just, for my computer, there's an actual thing that, above my numbers that says PRTSC for print screen. So if I hit control print screen and I went into here and then I pasted it, I can get my picture. Now I would have to crop this a little bit. Yours is not loading. Hold on. Let me, snap. Let me zoom in here a little bit. Okay, so not pushing. Describe in words. Equal forces, opposite directions. So in scene 2, we have Joe that is pushing but not moving the cabinet. All right, so if we go to the simulation, we got, it was a cabinet, or I guess it was cabinet. Oops. Well, the first one we were using a box. Whoops. Or a small crate. So we would click on this little down box here and got file cabinet. All right. So we have to apply some sort of force here. So it says we're going to apply force, but it's not going to move. Let's apply, let's say, a force of 50 newtons. Oh, that's way small. Let's go like 150. Okay. So you see that there is a force, F sub A, F sub F. What do you think those would be, per se? Let me see if I can make this just a tiny bit bigger without this thing moving. Okay. So F sub A, look how Joe is pushing on this thing. He's pushing to which direction, would you say? To the left or to the right? He's pushing to the right. And which arrow is going to the right? The F sub A. Okay. And then on the other side, we have something that's F sub F. If you're trying to push something, let's say to the right, and it's not moving, that means you have to, there's an equal force in the opposite direction, basically kind of canceling it out. So there's no motion going on here. So F sub A is something that we call the applied force. You may see it as F sub APP for applied force, and F sub F is friction force. So normal force, applied force, gravitational force, friction force. So same idea here. Print screen, control C that nonsense. Or shit, did I do that right? Nope, I didn't hit control print screen, did I? I hit control C. Control print screen. There we go. And now, bibbity boppity. Boop, double click on it, and let's crop this down a little bit. Let's give it some little expansion. Let's wrap that text. Oh God, no, no. Actually, wait a minute. Shit. It's being a scutch. It doesn't like to move very much. Okay, so it says here, okay, describe in, with the screenshots or describing words what's going on with the force arrows. You have F sub F. All right, remember how to get the subscript is control comma. It's got to equal F control comma A control comma to get out of it. So that's got to be accurate. And then also F sub G has got to equal F sub N. So everything's chilling. Everything's balanced out. Right now we have complete balanced forces. The net force on this thing is 0. What do you think net force is? When you hear the word net, what does that mean? Wait, what? Okay, yes, but not. How about like in pay? You guys work yet? Paychecks. You have net pay, right? Gross. So you gross a certain amount of money, but then a bunch gets taken out because of like taxes, right? And you're left with your net. It's basically the sum of what you have here, the sum of what's left. So if everything is canceled out, the net force is 0. If something doesn't cancel out, well, then you are going to have a net force in some way, shape, or form. Now, in scene 3, Joe is now pushing the cabinet and it's moving. So now I'm going to I'm going to increase this to, let's say, 350 should do it. Okay. Now what do you notice here? Yeah. This arrow is longer than F sub F. So do you think they're going to balance out? I don't think so. And if I hit play, now this thing is moving. So if I went to reset, oops, go back to file cabinet. What number did I have it at? Like 350? Okay. So print screen, or let's let it play for a second. Control. All right, I'm going to screenshot here. Okay, so what's going on here? Are the normal force and gravitational force still the same? These guys, yeah, they're still the same. But what else is going on? Is the applied force and friction force still equal to each other? Does it look like? I would say nah. So the applied force is, where's the greater button? The applied force is greater than that guy. So the first one, the gravitational force and the normal force are equal to each other. In this one, the applied force is greater than the friction force, so now we are going to have a motion. We're going to have some movement. Whereas over here, when everyone was equal, there was no movement. So with all of that being said, number 4 asks, describe what is necessary to start the file cabinet moving. So here, word we used was balanced. Here, everybody was balanced. Here, is everything balanced in the third? In the third scene, is everything balanced, or would you say it's unbalanced? Yeah, I would say it's unbalanced. So if that's the case, what is necessary to start the file cabinet moving? You can have some sort of combination of saying that there needs to be an unbalanced force, or that the applied force needs to be greater than the friction force. So number 5, compare the applied force arrow and the friction force arrow. What is similar? What is different? What is similar? What is different? What is similar and what is different? What do you guys think here? In number 6, use your answers to number 5 to say whether the forces are balanced or unbalanced in each scene. So in scene 1, everything is balanced. What about in scene 2? What do you guys think? I would say that, because there's no motion and everybody looks to have the same magnitude. And then in scene 3, would we think that is balanced or unbalanced? Yeah, I would say that as well. All right, I would say that that would be unbalanced. Oh, I guess you technically could have put it in this, but whatever. Okay, part 2, understanding applied friction and net force. How can you make the friction force arrow longer? How can we make the friction force arrow longer? So right now, I have what? Is there any friction or applied force? No. If I increase the applied force, notice what happens to F sub A. It gets larger, yes? Now notice what happens to the friction force arrow, though. It also got larger, right? So based off of that, how can we make the friction arrow longer? Just based off of what you just saw. Just the friction force in general. How can I make that longer? What am I doing? I'm increasing the what? Number 8, apply enough force to move the cabinet. Okay, so then it asks, what happens to the friction force arrow when you stop applying force? No applied force arrow. All right, so back into 7 for a second. How can we make the friction arrow longer, right? By increasing our applied force, we wound up increasing the frictional force arrow. You're looking at that and see? So there's going to come a point where you are going to apply enough force to overcome the friction force. The friction force is basically static friction force. There's like a set value, set number. It has to do with the mass of the object and the surface, whatnot. When you overcome that value, then we have kinetic friction, the coefficient of kinetic friction. And now that is much smaller. So once you get an object moving, it's a lot easier to get it to keep moving than it was to get it to start. And so here we got nothing, 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 and then somewhere around 220, 230, nothing happens. 235, 240. Oh, I'm pushing the box. That's why. Not the dog. I think it was about 225. Maybe a little bit more. Somewhere around like the 230, 240 range. Then you saw that the applied force vector got larger. I'm sorry, the applied force vector was at the same spot, but the frictional force jumped down because now we're looking at these little symbols down here, mu sub k, mu sub s, static friction coefficient, and kinetic friction. We'll get into that when we're doing Newton's second law. But for now, what happens to the friction force arrow when you stop applying the force? All right, so let's just reset. Let's go to cabinet again. And let's say we're going to 250. That's 350. So this should definitely happen. What happens to the friction force arrow? So right here, right off the rip, before I hit this thing starting, you can see that the applied force arrow is larger than the friction force. So that means there's going to be an unbalanced force and this thing is going to move. So then once this thing starts moving, watch what happens to the frictional force arrow. What happened to it? Yeah. Yeah. Okay, so what happened to the friction force arrow when you stopped applying force? So we got rid of, oh, I apologize. It was when we got rid of the applied force. Okay, so we have to go to the file count. There's a force where it needs to get bigger, okay, and now if I let go, I stopped applying force. Okay, slow down, buddy. Let's bring you back. Scoot. After you stop applying a force to it, did the friction force arrow change its size? So if I'm applying a force to this thing and then I let it go, does the friction arrow change its size at all? No, but then notice what happens. Once it stopped moving, the friction arrow disappeared. So I'm pushing, 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 pushing. Crap, it hit the wall. Once it stops moving, the friction force is going to disappear. So how would you describe friction force? And how would you describe the applied force? How would you describe friction force and how would you describe applied force? Notice what I'm doing right now, nothing. Is there an applied force and friction force? No. if I start to push it? Are there two forces? There's both. Okay, the harder I push, the more the applied force goes. If I let it go, there's no applied force, right? I'm not continuously pushing on it. Joe's not continuously pushing on it, so the applied force disappears. But since this thing was moving, come on, build up some speed. Okay, the frictional force is still there. And what direction is it going compared to the motion? All right, so this thing is going to be moving to the right, yes? What direction is friction? To the left. Okay, well, what if I'm pushing to the left? What direction is friction? So what can you say? Well, right now there is no applied force. Good. It's not necessarily opposite of the applied force. It's opposite the direction of motion. Okay, have him move a new object, and then how is this moving different than the file cabinet? Guys, we're going to continue here tomorrow. All right, we're going to continue here tomorrow.